magnitudes and phases of the voltage, because this voltage is given and a component of this voltage is flowing, is being delivered to this terminal. So that terminal is termed as V out. So we can also say that it is a sort of a transfer function in which the output is this thing and the input is this thing. So V naught by Vt is the transfer function of this circuit. So for all of these things, this equation is given Vt, in which the n is odd, and from 1 up to infinity the summation is given for sine terms as well as cos terms. So we can clearly see that cos terms are let's say a 0 degree terms, and sine terms are cos terms with a 90 degree shift. So these are the J components. So how will we find these things? We'll put n equal to 1, 2, 3, 4, 5, 6, but there it says that only odd components, so we'll put 1, 3, 5 and 7 in it, and we got these particular values. So these are the phasor, not in phasor form, so we convert it to phasor form by finding its magnitude and phase. The formula is simple. We use real square plus imaginary square and under the root to get our d1, and then theta 1 is tangent inverse imaginary by real. So we repeat this step after putting n equal to 1, 3, 5, 7. And once we get this phasor term, so let's say this is a 7.5 angle minus 22. So this is 0 degree and it is minus 90 degree, and here it is minus 122 degree. So its length is 7.5 and its degree is minus 122 degree. So for calculating the power, we draw up a shadow of vertical projection of this thing on this x-axis. So this projection is the cos theta projection of it, and this cos theta is actually cos of omega t plus theta, because it is not only an arrow that is in this direction, it is a phasor. And what does phasor do? Phasor rotates. So it is rotating with the speed of omega t, and it is already delayed by an angle theta, and we want to find its power. So power will be instantaneous. It will involve a cos theta and omega t as well. So there are 4 components of it. So all the components should have their own omegas. So this first one is having its component omega. Second one is having 3 omega, 5 omega and 7 omega. Now after we calculate these phasors, we want to write their equations. So if we write the first equation of it, so for that we calculate the omega. So what is the omega for this particular first part? For this we calculate omega from our Vt. Here we can see that this is 2nt. So if we put n is equal to 1, we get 2t. So 2t is actually omega t. Hence omega is 2. So the first equation and the first term will have this particular structure, but the angle would be minus 122, this omega would be 2, and this thing would be t. So putting omega equal to 2, we got 2t, angle 122, and it is a phasor of 7.5 magnitude dropped on this line. So it will be a cos, and it will have 7.t cos of 2t minus 122 degree. So this is the first term, and it is a bit clear now that how this term came. Okay, so we will apply the same technique on other terms as well. The second term is 2.2 angle 102. So it will be 2.2 cos of, now this is 3, so this is 3 omega t. 3 into omega is 6, so 6t minus, what's the angle? It is 102 degree. So the second term is this thing. The third term would have an omega of 5 omega, so 5 into omega is 10t, and what's the angle? 97 degree minus, and it is cos, and its magnitude is 1.3. So the fourth one is 0.91 cos of 14t. Why it is 14? Because there is a 7 term and omega is 2, so 7 multiplied by n equal to 2 is 14 minus 95 degrees. So we can clearly see that the magnitude has dropped significantly from 7.5 to 0.91. So 7.5 to this third term, from first to third, it is reduced by 5, and from third to fifth it is reduced by let's say 1, and to 7 it is reduced by 0.4. so this is an abrupt change like this. So we can prove our assumption that the power for higher term is lower. That's the main reason that we neglect the higher terms. So that's how we calculate the voltage. Now voltage is calculated, but the other term which is important is remaining. What is that term? That term is the current for this specific circuit. So current would have also those 4 omegas values. This is the solution for that. We are having frequencies in which, let's go to this section and see, is this equation is not having any DC term. It is starting from 1, so DC current is neglected because the DC voltage is not present. So voltage is 0, current is, if it is anything, the power dissipation would be 0. So if we go here and see, this I is V by R. This I is actually this thing, I. So I is V by R, and I is calculated from this voltage V divided by the resistance of all the paths. So what's the path resistance? 1 plus 1, 2. So 2 in parallel with 1 farad, which is 1 over j omega, and that is in addition with this resistance 2. So 2 plus parallel combination of 1 over j omega and 2. This is the path resistance, and it is calculated like this, that 1 over j omega plus 2 and its whole inverse. So how will we calculate it? It will go up this thing, so by 1, so we will have these multiplication terms up, and here we will have 2 j omega multiplied by 2, so we get this thing like this. So this is the current in this branch. Now we got our I current, so I is the total current. If you want to find the current in this output side, what we will do, we will use the current dividend tool, which will use the I1 current as its output, and it will use the I current as its input. So input is I, and the branch in which it is not flowing is 1 farad, which is 1 over j. 1 farad is 1 over j, and the branch in which it is not flowing and flowing is 1 plus 1 over j omega. So we calculate this thing like this. Not 1, 2. This thing is 1 plus 1, 2. Okay, so this is our I1. So I1 multiply V1 would give us P1. So this is omega. Omega is for first it will be 2 and 2. For second, not calculating. For third it will be 3 omega is what? 6. And then for fifth it will be 5 omega 10, and for 7 it will be 14. So same omega would be replaced in this equation which we calculated, this one. So we divide by 4 plus 4 j omega. So 4 multiplied by 1 is 4, multiply by omega 1 is 8, because omega 1 is 2. So first one is 8, then 6 multiplied by 4 is, this 4 is used everywhere. So 4 multiplied by 2, 4 multiplied by 6, and 4 multiplied by 10, and 4 multiplied by 10 is 40, 4 multiplied by 14 is 56, and consequent voltages are also used. So V by I, V by I, V by I, V by I. So V1, V2, V3 and V4, these are used. So we got these voltages for this output branch. So now we can write the V out as this thing. V out is equal to this plus this plus this plus this. So this is pretty much it, that we calculated the V out as separate frequency components. We can also calculate the current of the output side if we multiply this 1 with not current is calculated already. We just have to, okay, so current is calculated already, we just have to give the values to it to make this thing converted to power. So P would be equal to 0 voltage multiplied by I, which is 0. P1 would be equal to I1 multiplied by V1. So V1 is calculated in here. Similarly, this I1 would be placed from this equation. So this is the procedure. We will study this thing, the calculation of power, in our next example as well. So let's go to that example. So in this example we calculated what? We calculated the output voltages in terms of the input voltage and frequencies. As we can see in here, that in this we wanted to calculate the output, we wish to determine the output steady state voltage in terms of Vt. So we calculated that. Okay, this is an interesting example, example 15.8. In this example we have a sample circuit for which we want to calculate the average power absorbed. So average power absorbed would be the absorbed power by resistance, capacitance and inductance. These all three things are available in here: the resistance, the inductance and the capacitance. Okay, so this is the input signal for us. We are having a non-cos, non-sine signal. This thing is our DC voltage. This is a 377 omega equal to 377 signal, and this is omega equal to 754 signal. This is radian per second, radian per second. So first we calculate the power for, or the current for voltage 0. So here we are having omega equal to 0. So if omega is 0, this circuit would be open circuit, hence I0 would be 0. So if I0 is 0, P0 is also 0. So there is no dissipation for this current 0. Okay, After that, we will calculate the current for a frequency of 377. So for 377, we first calculate the XC and XL. So XC and XL turns out to be these things. We are already having resistance in terms of R, so this whole path would be R plus XL plus XC. So I is equal to V by these things. So what is the V in this case? Since we are calculating it for 377, so V would be 16 angle 30 degree for it. So for that we got I equal to this thing. If we multiply this I with this voltage, let me write it with some other color. If we multiply this I with this voltage or this voltage, we will get the power dissipated at 377 radians per second frequency. So this is 16, this is 0.4 divided by 2, and cos of what was the angle, the initial angle that's written in here, and the angle that is added due to this component, so that is also subtracted. So cos 30 degree minus 799 is the difference between the current and the voltage angles. So this is written in here. After that, we are left with the 754 radians per second frequency. So for 754, we calculate XL and XC as well. So XL and XC are calculated, and after that V by Z is calculated as I, and this I is multiplied again with V and divided by 2. So I turns out to be 0.75. 0.7 multiplied by what's the voltage at 754 frequency. So that voltage is 12. So multiply by 12 divided by 2, and what was the angle of voltage, that is 20, and what was the angle of current, that is minus 26. So both are added, and then the cos terms are solved using calculator or anything and added up to get the total power. So for this specific signal we got this much power.